Thank you. It is really a pleasure to be here, and I'd like to thank the organizer for organizing this conference, and particularly my talk after Pascal. So she really saved me a lot of effort to explain some of the things we do. But I also want to point out a lot of our model development that we will present later actually already benefit a lot from their laboratory experiment. But I just want to also point out we are not able to simulate the last part, which is the water saturated condition. So don't put your hope too high. For this talk, I'd like to talk about sort of the importance of resolving turbulent coherent structures in the modeling of frontal features in estuaries, and also give you two coastal sediment transport application. And this talk is a summary of several PhD student, postdoc, and researchers' effort in both at the Center for Applied Coastal Research in University of Delaware and also Grenoble. Particularly Tian-Jian Hsu, he's our long-term collaborator on joint development of this two-phase model for sediment transport called SATFOAM. And Tian-Jian Hsu, he's my long-term collaborator on eddy resolving coastal modeling. So to start, I will argue that for coastal and estuary community, the so-called Reynolds average approach is still the most popular and affordable modeling approach. The main assumption, however, in the so-called Reynolds average approach is that it models the effect of turbulent fluctuation on the resolved mean flow using a diffusion process, and hoping that this diffusion is doing a good job to the resolved mean flow vortices, for example. This actually has been proven to work pretty well if you have simple, so relatively simple shear flow condition. However, it is also shown, and I'm going to show you some example today, that when you have a more complex flow, such as encountering instabilities, or when you have primary vortices generated due to flow separation, then this sort of a forced separation between the resolved vortices and the subsequent energy cascade actually become ambiguous. And I'm preaching to the choir here. I'm pretty sure you will agree with me that in this kind of situation, you will use, for example, the large eddy simulation to resolve these nonlinear processes. Of course, the drawback is that then you have a higher computational cost. And moving to more complex situation where you have density stratified flow or you have particle-laden flow, I think turbulent diffusion type of concept for the subgrid parameterization is even more questionable. And this is even true for some of the large eddy simulation application. For example, in some of the coastal application, I think it is still sometimes impractical to use a filter size, which is usually your grid size, that's close to the Osno-Dolph scale. So in this case, if you use simple diffusion for your subgrid closure, you may not be able to capture the subgrid stratification effect. For particle-laden flow, you have two possibilities. On the one hand, typically for fine sediment that we are interested in, we may have the grid size, the filter size, that is still much larger than the particle size. So in this case, your subgrid closure have to rely on, have to kind of deal with the unresolved microstructure. Or on the other hand, you could have situation where your filter size is smaller than the particle that you are interested in. Typically, we encounter this for quartz sand. In this case, you need to worry about the so-called finite size effect, or probably should use the fully resolved approach. So those are the challenges that we are facing. But of course, today I'm not going to focus on discussing the closure for the multiphase flow, but instead what I want to focus on today is to show you a few examples in which for coastal application that resolving the turbulent coherent structure is really, really important. And unfortunately, the conventional Reynolds average approach is not going to work. I'm going to first talk about the generation of the lobe and cliff instability at a field scale river plume using a non-hydrostatic coastal model NH wave. And then for the next two applications, I will use a two-phase model for sediment transport called StatFoam to essentially use large eddy simulation to simulate the two very interesting sediment transport problems. So this NH wave actually solved the three-dimensional south stratified density varying flow with Busnik approximation in the so-called terrain and surface following the so-called sigma coordinate system. So if you're familiar with similar model like SUN10, it is a pretty similar model, but usually SUN10 is designed to run based on the Reynolds average formulation. But here we specifically designed NH wave to be a eddy resolving coastal model. And the reason I'm hesitate to say large eddy simulation, instead I just say eddy resolving, is because in a lot of the application, we are not able to afford to have a grid size smaller than the Orthodox scale. For example, in one of our earlier simulation, we're simply simulating a Boolean density current in a laterally uniform channel. We're comparing Reynolds average capsule model with this, so I call it coarse grid LES because in this case, the grid size is about 3 times larger than the Orthodox scale. So what you can see here is that even with the coarse grid LES, we can still kind of resolve the sort of the braid, if you want to call it, the onset of the Kelvin-Helmholtz instability. On the other hand, if you use the RANS model, because you have a very big diffusion, so what you actually see is just a very smooth out mixed layer. And so there's much less structure there. But overall, in this case, if you look at the average mixed layer thickness and the overall plume behavior, I would say the coarse grid LES and the RANS model kind of give you a similar feature. However, if we use a much higher resolution to run the same problem, in this case, our grid size is similar to the estimated Orthodox scale. And what you can see here is that the model is now able to, so I will call this as a LES now. You can see that the model is able to resolve the generation of Kelvin-Helmholtz instability. And more importantly, their subsequent collapse into more of a 3D coherent structures. The model is able to do it. However, if you look at just at the front here, you see that the flow seems to go back to more of a non-turbulent situation with less feature at the front. And of course, this kind of feature is very different from what you see in the field condition. The lab is a thermal image reported by Horner, Devine, and Chickadell, where they observed the so-called lobe and cliff instability at the front of the, in this case, is the Merrimack River. Okay, you see this nice lobe and cliff feature at the front. And recently, this is just a drone image showing some kind of shear instability at the front of Connecticut River plume interacting with a very strong shear current. So today I'm going to focus on explaining this first type of frontal feature called lobe and cliff. What made this problem really interesting or fascinating is that the classic explanation for the lobe and cliff instability for the so-called no-slip bottom boundary cannot be really used to explain what we see for surface river plume. The classic theory based on Simpson and I believe Hartle, this is the work also involved Akar, that the DNS basically show very clearly for density current on the no-slip boundary, you have the arrested nodes. This allows the less dense fluid to get entrained underneath, and then locally you can trigger the Rayleigh-Taylor instability. That's the cause of the lobe cliff instability. However, for river plume, we usually model the free surface of the river plume as a free slip boundary condition. At least we're not going to model it as a no slip boundary condition. So here we hypothesize that turns out the lateral spreading of the river plume actually play a very important role in triggering this lobe and cliff type of instability using the numerical simulation. So here we're carrying out a pretty intensive simulation. We have a domain about 0.5 kilometer wide in wide and length. And then I think we're using like 100 million grid point. And so we are able to resolve having a grid size close to the orthodox scale. And here, let me play this again. Actually, we don't have to. So basically here you can see that if you look at the side view of this plume, we can resolve the Kelvin-Helmholtz instability reasonably well, and also the head of the density current. And also this one I want to play again is that this is tracking the front. You can see that our model is also able to predict this wiggling, or if you want to call it lobe and cliff feature. So here I want to do some more detailed comparison. So the top panels are the thermal image from the observation, and the bottom panel are the modeled image. The color at the top panel is based on is following the temperature, and the color in the bottom panel is based on salinity. Essentially, our model is able to resolve this kind of lobe and cliff similar to the field observation, except that our models slightly overpredict the wavelengths of this lobe and cliff. However, if you look into another important piece of information, this is measured vertical vorticity calculated based on the surface velocity field. And what Horner-Devine and Chickadale report was that interesting thing is that in each lobe, you have the existence of this counter-rotating vortices. And this important feature is also captured by our numerical model. We also have a pair of counter-rotating vortices. Horner-Devine and Chickadale hypothesized that the existence of this counter-rotating vertical vortices is because of the existence of stringwise vortex tube. Okay, this kind of stringwise vortex tube that actually get bended upward close to the front of the river plume. So that's why you see this counter-rotating vortices. And for that reason, because of the counter-rotating tube, for that reason, you see that at the lobe, you must have a downwelling. Okay, and then at the cliff, you have upwelling. But if that's the case, the cliff should be associated with upwelling of cooler fluid, denser fluid. And just want to show you that indeed our simulation also showed that there's an upwelling of denser fluid. And so now, if I convince you that our model is doing a good job in reproducing the observation, now I want to use the numerical model to explain why there's this generation of stringwise vortex tube. So here is a visualization of turbulent coherent structure using simply the Q method. What you see here is that 80 meter downstream of the leaf-out point, you see this relatively laterally uniform rollers. This is basically the Kelvin-Helmholtz instability. But as you move further downstream, you start to see more lateral variabilities. Eventually, at 150 meter, you see the generation of this sort of a meter scale lateral instabilities. That's pretty clear here. And then further downstream, you see that this instability actually connect to the next roller, eventually leading to this more stringwise, parallel stringwise streak, eventually attached to the front. And in fact, if you look at this is the vorticity equation for the generation of stringwise vorticity. If you look at the the three terms that can generate the string-wise vorticity. Well, if you look at this term, this omega x is associated with Kelvin-Helmholtz, the vorticity generated by the Kelvin-Helmholtz sensibility. While the vorticity equations tell us that has to interact with the lateral gradient of string-wise velocity in order to generate vorticity in the string-wise direction. And of course, here where our plume is laterally spread. So we do have a lot of lateral variabilities. And anyway, so in summary, we believe that lateral spreading is the key to generate the string-wise vortex tube. So essentially converting this 2D sort of a lateral vorticity due to Kelvin-Helmholtz instability into more 3D structure. And you can only capture this with 3D large eddy simulation. You cannot capture this with Reynolds average approach. And now I want to move on to the second part of the talk, that is to use a Eulerian two-phase model called SAFON. I'm going to carry out large eddy simulation to address two sediment transport problems. First, just want to mention SAFON is an open source Eulerian two-phase model for sediment transport created in OpenFOAM. And it's very important for me to point out, SAFON, the creation of SAFON is because of the KITP. Because back in 2013, both my collaborator, Julian Schuchet, and I, we stayed here for a month in 2013. And 1 month is really a long time. We get to talk a lot, become good friends, and we talk about our big dream. We want to create this open source model for sediment transport, for sediment transport community. So after the meeting, we really worked together. And thanks for the KITP and ACAR. And since then, we have created SAFON. SAFON essentially solved the water phase and sediment phase mass and momentum equation with the coupling terms. And thanks to Pascal, I don't think I need to repeat some of the detail there. It's pretty similar to what Pascal was saying. Essentially, we have the interface coupling due to drag and pressure gradient. And for particle stress, for shear-driven collision, we have two options. We have kinetic theory, and we also can use mu-I rheology. And for more quasi-static frictional contact, right now we're using more simple Johnson-Jackson type of formulation. And recently, we also added dilatancy by Julian's postdoc. And we've actually validated a model for the granular collapse for the complete submerged situation. But I have no idea how to model your water saturated condition. That's definitely an important future work. And I just want to point out, the good thing about using a two-phase model is that we can avoid the artificial separation of sediment transport in the bedload and the suspended load layer, as many typical single-phase sediment transport model has to do. The earlier version of SAFON is based on Reynolds average approach, but today I'm going to focus on 3D large eddy simulation. So this is the Kavli equation we use, filter two-phase equation. The important thing I want to point out is that for the closure of a fluid and the particle subgrid stresses, we use a dynamic procedure. And for the application I'm going to show you today, we are able to have our grid size very close to the particle size. And so for the application I'm going to show you today, because of that, we actually ignore so-called the other subgrid contribution because our grid size is very, very close to the particle size. I want to look at an application called sheet flow. What is sheet flow? This is a picture of it. So essentially, sheet flow is a sort of a dominating mode of sediment transport, particularly in the coastal surf zone energetic environment. In this case, your non-dimensionalized bottom shear stress called shear parameter usually is much greater, or at least greater than 1. However, researchers in coastal processes has long been puzzled by this very unique sheet flow feature only for fine sand, which is very, very different from medium and the coarse sand. So when I say fine sand, I'm talking about grain size usually smaller than 150 micron. And two information here. The first information is that here you're looking at the sort of so-called net sediment transport rate driven by a onshore velocity skewed wave. So what is an onshore velocity skewed wave? Just imagine it's a Stokes wave, okay? And so this onshore velocity skewed wave is supposed to drive onshore sediment transport. At least that's the case for median sand and the coarse sand. However, laboratory measurement always show that for fine sand, the transport rate is negative, it's offshore directed, okay? And this is usually attributed to the so-called phase lag effect because they said the fine sand has a very small settling velocity. However, we always think that it is a little bit more than that. It should be a little bit more than that because there are also laboratory evidence showing that if you look at normalized shear flow layer thickness plotted as a function of shear parameter, for fine sand, you can see the scaling law says that the shear layer thickness is much larger for fine sand. So we think that these two must be also related. And just want to point out that I've been working on this problem for 10 years. Early days when we use Rand's model, it doesn't work, okay? And so now we're going to use LES, and our hypothesis is that we said we believe that the unique fine sand feature are caused by flow instabilities, not just the small settling velocity during the transport processes. And so I'm going to show you 3D LES. We are looking at 6 different flow configuration. This is based on 2 different laboratory studies for median sand and the fine sand. But I like to focus more on the first 2. That is simply driven by a sine wave, in which we have much more detailed model validation. This work has been published recently. So first, just want to mention that here you look at the comparison of measures, which is in symbol concentration profile under different phase of the wave crest versus the LES data. The left is the median sand, the right is the fine sand. While overall you will see that while the model is doing a good job, okay, but more importantly, you see that the model is able to capture for fine sand this very unique sort of a shoulder-like concentration profile feature, which do not exist for median sand. Also, the overall transport layer thickness for fine sand is much larger than that for the median sand. So the model is able to capture that. Also, if you focus on the this is the offshore-onshore flow reversal. That's this moment, okay, offshore-onshore flow reversal. You see that for median sand, most of the sediment that was suspended in the previous wave has already settled back to the bed. That's why when you look at the isosurface of concentration of 8% and 57%, they basically coincide with each other because they are all settled. But you do see some residual turbulence there. However, if you look at fine sand, you see that sediment are still mostly suspended because the 8% isosurface and the 57 isosurface still have a significant gap, okay? But there's really not much of a turbulence in between. If we go to, if we go to the acceleration phase, what you see is that flow become more energetic, so we have more turbulence for median sand, but still a little bit suspension, but the suspension is still quite small. The transport layer is still quite small. However, importantly for fine sand, what you see is that not only the transport layer thickness is large, you start to see this kind of a roller feature. This suggests there's roller instability that's actually occurring at this phase. And then when you go through the next phase, once you go to the wave crest, you see that this roller sort of exploded and then suspends a lot of sediment and generates a lot of turbulence. And at this moment, you see the transport layer thickness for fine sand remains to be larger than that of the median sand. And finally, at the deceleration phase, now the shear layer thickness for the fine sand is really reaching its maxima, and we see very energetic sediment transport. So, in summary, we think that the so-called phase lag effect for fine sand is not just about small settling velocity. It is also about the fact that the shear layer thickness for fine sand has been sort of significantly expanded because of the occurrence of instability. And that's why Reynolds average model couldn't do it, because you cannot simulate that generation of instability. And because of the time, I'm going to go faster now. Just want to point out that we then drive the model with a onshore velocity screw wave, like a Stokes wave, and showing that, again, for fine sand, the same situation occurs under the crest. You have an expanded shear layer thickness, instability, that leading to a lot of sediment suspended during the crest actually gets swept offshore. That's why you see a net offshore transport under an onshore velocity screw wave for fine sand. This is really important for coastal engineering. I want to use the last 5 minutes just to talk about the second application. This is about scour around a vertical pile driven by an oscillatory flow. The vertical pile is usually an idealization of, for example, bridge pier or the foundation of a wind turbine. And it is well known that the scour around this kind of vertical pile is directly related to the generation of different type of coherent structures around this structure. And so now our concern, and so what I'm going to show you is that I'm going to carry out a 3D large eddy simulation versus a 3D Reynolds average simulation with a K omega model. The concern here is that in the Reynolds model, we artificially separate the resolved mean flow from the energy cascade of the vortices, which is a nonlinear process. But in this problem, even in the so-called resolved mean flow field, you still hope to be able to resolve the primary vortices, because otherwise you're not going to have scour. So the question right now is that if you use the Reynolds approach, you model this highly nonlinear cascade process as a turbulent diffusion. Is it good enough to make sure the resolved primary vortex in the Reynolds model is strong enough to trigger the scour? Okay, so of course we try to answer that by simply using large eddy simulation first. So here is the animation of the simulation for large eddy simulation. This is not a very energetic wave. Okay, and so the Kc number is only about 10. The shear parameter is only about 0.1 if you remove the cylinder. So we're supposed to see some ripples. But important thing is, you see, the LES really allows the generation of different type of coherent structure, what you see here. And this coherent structure certainly triggers a lot of the scour. Okay, and if you compare with the sort of time development of the scour hole depths with the measured data, the measured data is this black curve, which Sumer is the measurement. He fitted with an empirical curve. But you can see that the LES predicts scour depths that's pretty consistent with the measured data fitted with the empirical curve. On the other hand, if you look at the blue curve here, this is the simulation from the Reynolds average model. You see the problem here. There's a significant under-prediction of the scour depths using Reynolds average model. And the good thing about this data set is that Sumer also measured the time average bottom shear stress distribution around the vertical pile. The symbol is the measured data. What you can see here consistently is that if you use Reynolds average model, either you use Cephon or you use the reported by an earlier study, they always under-predict this sharp increase of bottom shear stress very close to the pile. On the other hand, if you use LES or there's a DNS study for this problem, that you have no problem. You can really resolve this sharp increase of shear stress. And what is the reason for that? We can easily find out the reason, at least qualitatively, that if you just simply visualize the turbulent coherent structure for the result based on Reynolds model and the result based on large eddy simulation, you can clearly see that using the same Q number The LES shows all kinds of coherent structure, including this so-called horseshoe vortex generated around the pile. Using the same Q number, you see nothing here. So this means that Reynolds average model, indeed, as we afraid, that you have basically your subgrid closure additive viscosity has too much diffusion. That kind of smooths out some of the important vortices that you are supposed to resolve. On the other hand, for LES, since you only deal with use diffusion at your subgrid, which is close to the grid size, so that you still can preserve the vortex that you're trying to resolve. So take-home message, I would say at least for certain coastal processes, using diffusion may not be the best solution. It shouldn't be our excuse for coastal modelers to use diffusion. You really need to look at different problems, and we argue that the next generation numerical model, at least for certain type of coastal processes, should be based on turbulence resolving simulation in order to tackle the nonlinear turbulent processes. And just want to quickly mention that we are continuously developing SATPHONE for backbone simulation, for coupling with the moving object in order to do skull burial. And then we also add a free surface to our model so that we can expand our application to more wide spectrum of different applications. Thank you.
Thank you for showing us this beautiful simulation. Okay, so many questions, I hope. Yeah.
Thanks, Tom. Very nice talk. I was wondering, your SATPHONE version that you use, does that account only for bed load transport, or do you also fully suspend sediment?
Yes, both.
Both, okay.
Both. So essentially, because of the two-phase approach in which we resolve turbulence, in the meantime, we also have, maybe let me just go back to the, well, first just want to point out, you see the way we model the concentration profile, we can model the sediment concentration all the way from the settled bed to the very high concentration regime dominated by the contact load, to a lower concentration regime maybe dominated by mu-I rheology, kinetic theory. And then this part of the transport is really dominated by turbulence, turbulence suspension. So they are all one single system. And I think that's the advantage of using a two-phase model. It's just that we don't resolve the grain interaction.
Right, but so you have an empirical condition for the erosion threshold and so on?
Nothing, we don't have that. It's just a settled bed. And of course, the amount of sediment that we can suspend based on turbulence and the amount of shear depends on mu-I rheology, depends on kinetic theory. So the stiffness of the bed is certainly controlled by other closure, mostly in, and that's why I'm glad in this talk, I don't need to explain it. It's the earlier part of today's talk, yes. Okay. And that, if you do it right, that allows your sediment get suspended by shear, basically.
Thanks.
I'd like to return to this question. That's what I was wondered. So there's no empirical correlation that you use for entrainment of the particles from the bed. Okay, that's good. So in other words, you model the bed itself as well,
that's right?
And to what extent is the fluidization of the bed important?
You mean how we model the fluidization? You mean
yes, the sediment bed must be fluidizing if there is a pressure difference.
Yes.
And as a result, it can enhance the entrainment. So is that naturally in this rather powerful model that you use, this powerful method?
How natural, I don't know, but it's part of the closure that we use. So for example, it's really this part. You're asking an excellent question, by the way. So the important thing here is that if we have a turbulent shear flow that drives the shear, and then that shear is going to be filled because the particle is also going to move. So particle is going to have a shear. That's going to first drive the shear-driven collision, whether you use mu-I rheology or kinetic theory. And then And then once you further go into deeper part of the bed, usually it goes to about 57% in random loose packing. That's where the Johnson-Jackson, at least in our closure, kick in. So the Johnson-Jackson, essentially the way I see it, from a less analytical way of looking at Johnson-Jackson, is more of a modeling the elastic behavior of the bed, such that it depends on concentration. So the idea is that if you have a very high concentration, you're gonna trigger larger particle normal stress, particle pressure. But remember, that particle pressure gradient is gonna balance with the immersed weight. So that's how you can have a settled bed. Okay, but that particle pressure, very large, it's gonna kick into this Sanderson formulation, which is essentially a Coulomb type of formulation that link the particle pressure with the shear stress through a friction angle. And so that's how you also can deliver the shear further into the bed if it's sufficient enough. But once you have shear, then you trigger suspension. So there's this sort of an iterative process going on there at the bed. That's how it works in our model. It's not perfect. For example, when we recently tried to apply this type of model to look at some liquefaction problem that you really need to deal with the high concentration part of the bed, it tends to be less stable. And so we're still working on how to improve this part. But for those kind of applications, essentially you have a bed, you have a shear-driven flow, this type of formulation seems to work pretty well.
I have a question. I have one. Okay. So basically what you can do is change your closure whenever you want, more or less. You can use kinetic theory of mu of I. So you can use it also for laminar flow, I guess.
Yes, totally. In fact, this part I didn't show you. Our model has been pretty much everything that Pascal has shown. We went through those benchmarks, many of your experiments.
Okay.
In this case, we turn off the cold turbo. We basically run laminar flow, and then we turn on new rheology, make sure we reproduce exactly what's, including those analytical solutions that you mentioned.
Okay, and the drag also you can change, I guess, the coefficient of the drag.
Right, you can use different. I mean, you can use different closure if you want. And so that's why, this model is open source. Anyone here, if you are interested in testing whatever closure you have, you can go download it.
Okay.
If you have any questions, send Julian or me an email.
Yeah.
And this is really what we hope. We hope to have this little program, like you can do a plug and play to whatever you like, and testing with benchmark or whatever interesting case you are interested in.
Thank you.
Yeah, a very general question. I learned a lot from your talk. It's interesting. Perhaps I missed it. The Osmodov scale that's characteristic or typical for your problems is
for typical river plume, I think it's like 10 centimeter.
Oh wow,
very small,
really small.
That's why we're not able. So far, I have no simulation. So far, I can resolve the Osmodov scale. I can be close. That's why I don't even want to say large eddy simulation, because sometimes people will just say, "Oh, this is not large eddy simulation." Yeah.
Well, in our field, we say large eddy simulation with no shame.
That's why I love you guys. I told you very much, right?
but I mean, I just did a quick kind of back of the envelope estimate. At top of a stratocumulus cloud, Osmodov scale is about 1 meter. Yeah. And even the best LES are probably 10 meters or 30 meters. So. Yeah.
Right, you can almost see that because you see the cloud evolving very slowly. But if you look at the shear instability in ocean, especially in the estuary, I'm talking about, when I say ocean, I'm sorry, I'm really talking about estuary, coastal.
Yeah.
They are much fast time scale, so it's challenging for us to be able to resolve it.
Jim?
Hi, if I understood correctly, you're saying that you can get lobe and cleft with a slip boundary condition, but it has to be radially spreading. Is that?
So can you say that?
I was asking about the earlier part of your talk with lobe and cleft instability. So you're saying that you can get them if you have a slip condition, but you think radial spreading is necessary.
That's exactly what we do in our simulation. Our numerical simulation, there's question, if you ask Horner Divine, he will say, who knows, in the ocean, maybe you shouldn't apply a no-slip boundary, free slip boundary. You can have wind, you can have wave. That's all true. But the good thing about numerical simulation is that we literally apply free slip boundary condition. And so whatever we see here, we're trying to understand why. And now we get to the point we believe it's because of the lateral spreading.
Okay, I think I've seen them in DNS without lateral spreading with no slip. So I was wondering if you'd seen them without lateral spreading, but I guess you're saying no. But I think you can still get it. Yeah, that's a good question. So far, I don't see it, because if you remember the first part of my talk, this is an example where I don't have lateral spreading. And this is the front you see. I wouldn't say it's completely lateral uniform, but it's much more uniform than when you have lateral spreading. So I guess, relatively speaking, I think lateral spreading definitely helps. But to answer your question, whether in a completely lateral uniform situation, you cannot have frontal features, I'm not so sure. There could be other type of, I'm not an expert in the stability analysis, there are other type of instability. There's even, I think there was a classic oceanography paper saying that the roll up of the Kelvin-Helmholtz instability provides a possibility of radiator instability. So, but then you have to have additional terms in your vorticity equation to generate that. So there are all other possibilities. I'm not trying to exclude other possibilities. I'm just trying to show, I guess that's a good thing of a model, right? You put in how much salt and sugar, you know what you put in, so you get to conclude. Thank you.
Yeah, thank you.
Any other question? Okay, we thank Tom a lot.